So hello everyone, my name is Xintong from Alibaba Cloud, and today I'm going to talk about Flink agents, the Agentic AI framework based on Apache Flink. Well, we all know that generative AI and agentic AI are very popular topics today, and some people even say that 2025 is a year of AI agents. And there are also a lot of AI agent frameworks out there, like the LangGraph, like Llama Index. Those frameworks help you to build agents. So let's start with the first question. Why do we create another agent framework? And how is it different from the existing ones? Well, the answer is we are targeting a specific type of agents, which we call it event-driven agent. And what is event-driven agent? So today, the most AI agents that you can see are conversational. So AI coding, chat BI, deep research, they all follow the similar pattern. Well, typically, user types their questions and requests in a text box and using natural languages, and then the agent will be triggered to perform the task. But event-driven agent, on the other hand, well, it are triggered by continuously generated real-time events generated by a system. So those events can be an e-commerce purchase, a live stream comment, and a web page click, or a sensor read from a self-driving vehicle or IoT devices. So, and as the AI techniques keeps evolving and become more and more mature, we expect that there will be more workloads triggered by system events rather than triggered by user requests, because events can be generated by systems with a way larger amount and higher frequency compared to user requests. So let's start with a few examples to see how event-driven agents may look like. So this first example is a live stream assistant agent. And during a live stream, there are usually some real-time comments from the audience, and the more popular the live stream is, the more comments it gets. So these comments are helpful for learning the feedbacks and adjust the live stream contents in real time. And however, it's hard for the host to read all the comments and analysis all in the real time. So currently you need a backstage team to help you with it. But with the event-driven agent, you no longer need this backstage team, because we can process all the comments in real time and calling LLM models, large language models for sentiment extraction and information summary and generating adjustments, suggestions. So for example, the agent may tell you that the most interested questions from the audience, or combining the audience profiles, it may suggest you to play some music that is liked by your audience most. And another example is the AI Ops agent. So taking Flink as an example, in Alibaba Cloud, we already have some tools that keeps monitoring the metrics and errors from the running Flink workloads and making diagnostics and taking actions. But these tools are currently built with rule-based, so that sometimes it's insufficient. Taking this example, so the task manager heartbeat timeout is a very frequently observed issue in Flink, and it can caused by different reasons. It can be a long JVM GC pause, a network disconnection, or maybe just a Kubernetes eviction. And each of them requires different diagnosing approaches and solutions. So currently, such kind of issues are troubleshooted by human manually. But with the event-driven agent, we can have the agent looking into a knowledge base that is full of operation experience, and based on the knowledge, the agent can leverage tools like log search or node health check to make the diagnosement. And furthermore, the agent can suggest operation actions, for example, just to report the issue or just to rescale the job. And depending on the risk level, the agent may just perform the action directly or ask for human confirmation before doing it. So now we have seen 2 examples of event-driven agents. Let's think about this next question. What are the common requirements from the event-driven agents? Well, firstly, the agent should process the events in real time. So think of our examples. The events, the live stream comments, job metrics, and arrows, they are all generated in real time. And also the adjustment suggestions and also the job operations, they are valuable only if they are performed in real time. So real time is the first thing. And second thing is scale. So the agents need to be capable of processing large amount of inputs because the volume and the frequency of the events generated by systems are way more than the user request. So we probably need distributed processing. And the stability. Unlike conversational agents where if anything happens, you can just retry the request. Well, for event-driven agents, they are usually long-running. They are running 24/7 and typically unsupervised and distributedly. So there's a high demand for the stability and fault tolerance capabilities. And data processing, so remember in the 2 examples we see, I think I forgot to mention that. In the figures, you will see that there's blocks in blue and in orange. Those blue blocks are just traditional data processing, and those orange blocks are just AI model processing. So typically in application, in the whole pipeline of your application, you will need them both. And also the connectivity, so the agents needs to process events from different systems, different sources, so it's important that it can connect to different systems. So now we need something that is that can process in real time with large amount of data and is stable, is capable of data processing, and it has good connectivity. So does this look familiar to you guys? This is exactly what Flink is good at. So Flink is the most powerful real-time processing engine. The processing latency can be as small as a millisecond level, and Flink can process as much as tens of millions of records per second with thousands of parallel tasks. And Flink is famous for its mature state management and checkpointing mechanism, which ensures fault tolerance with exactly one's consistency. And as a data processing engine, of course, Flink is good at data processing. It provides rich support for defining data transformations with its data stream API, table API, and SQL languages. And also, Flink has a rich connector ecosystem. There are tens of connectors maintained by the community, and even more third-party supports. So this is why we think that Flink is a good fit for building such event-driven agents. And this is also why we created Apache Flink agents. So Apache Flink agent as an open source framework for building event-driven streaming agents. We initiated this project in early this year, probably June. And just yesterday, we released the first preview release, Apache Flink agents 010. So now let's take a look at how Flink agents looks like. And this figure shows the architecture of Flink agents. We provide the agent native concepts and primitives such as large language models, prompts, tools, memories, just like any other agent frameworks. So building agents with Flink agents would be no difference from using any other framework. It requires no extra learnings. And we provide APIs in both Python and Java and supports both building agents with both the React mode and the workflow mode. And a wide and extensible ecosystem integration will be supported, including built-in implementations for mainstream model provider supports and tools and storages. And also there's APIs that allow you to have custom implementations. And we have a Python runtime, which is suitable for lightweight local execution for developing, testing, and debugging purposes. And we also have a Flink runtime for distributed and reliable execution in production. So this comes with the full state management and fault tolerance capabilities of Flink. Okay, now I'd like to show you how building agents with Flink agents looks like. And let's start with a workflow style agent. So as I have mentioned, we provide both Python and Java APIs, and I will use Python APIs in these examples. So to build an agent, the first thing you need to do is to define your own agent class, which should be a subclass of the agent. And here I will just call it my agent. And an agent consists of two fundamental building blocks, which are actions and events. So here we have defined an action called process input. As you can see, the action is just a decorated static method. So actions are triggered by certain types of events specified in its decorator. And here, input event is a framework built-in event that carries the data from the input data stream or table. So the action takes the triggering event as an argument, and may also emit new events in order to trigger other actions. And if an output event is emitted, the framework will convert it into a record and output it to the downstream data stream or table. And you can, inside the action, you can also access the memory. Okay, to chat with a large language model, we need to first define a chat model connection and a chat model setup. A chat model connection is a connection to the model provider and typically shared by multiple chat model setups. So here you can specify some connection-wide parameters like the service URL, access token, request timeout. And to define a chat model connection, here we create a static method in our agent class with the chat model connection decorator, and the method should return a resource descriptor, describe the class to be used and the parameters. So think of this as some kind of connector. Here we create a Ollama chat model connection. And then we define a chat model setup that references this connection. So this is where we define the chat-specific settings, like which model from the provider to be used, and the prompt, and the available tools, and also the temperature. So typically, an agent may have multiple different chat model setups, and they all share the same chat model connection if connecting to the same provider. Then in our actions, we can chat with the model we just defined, leveraging the built-in events. So we can emit a chat request event that references to the chat model setup we just defined and carries the chat messages. This will trigger the framework built-in actions to call the model and deal with potential tool usages. And once it's completed, the response will be replied with a chat response event. So we can create another action that monitors this event and process the response. So currently, we provide built-in supports for Anthropic, Ollama, OpenAI, and Tongyi chat models. And you may also add custom supports by implementing the chat model connection and chat model setup interfaces. So next is prompts. So there are three ways you can define a prompt. So you can create a prompt from a piece of text or from a list of chat messages. And in both ways, you need to define a decorated static method in your agent class that returns this prompt. And you can also leverage prompts hosted on the MCP server. And to do so, simply define an MCP server with a decorated static method, and the framework will retrieve the prompt from it. So by the way, the reason we need this static method is because Python decorators do not apply on the properties. So alternatively, we can also provide we also provided APIs that allow you to register the prompt and other agent components without using static methods and decorators. So I'll show you later. And tools are similar to the prompts. You can define a Python or Java function as a tool. And by adding this tool decorator, notice that the framework is automatically parsing the docstring to understand what this tool does and how to use it. And you can also leverage a tool hosted on the MCP server. Another frequently needed function is embedding and vector store. So using an embedding model is similar to using a chat model. You may define an embedding model connection, which can be shared by multiple embedding model setups. And in the first version, we provide built-in supports for the Ollama and OpenAI embedding models. And you may also add new supports, custom supports, by implementing these two interfaces. And then we can define a vector store and specify it to use the embedding model setup we just defined. So to search from the vector store, we can send a built-in context retrieval request event. And this will trigger the framework built-in actions to generate the embedding vector from the query text and use the vector to do similarity search from the vector store. And the result will be replied with a context retrieval response event. And notice that the action here listens to both the input event and the context retrieval response event. So this means either of the events can trigger this action. And currently, we have only supported Chroma vector store. And of course, custom supports can be added. So once we have defined our agent, we need to integrate it into a Flink job. So think of our agent as a large and complex custom operator of Flink. So it can read the input from a data stream or a table and generates the output as another data stream or table. And this is how it looks like. Simply use the agent's environment from data stream or from table and apply the agent and call to data stream and to table. And here the agent environment is something similar to what we are familiar with, the streaming execution environment. So in this way, we can easily and seamlessly integrate the Agentic AI pipeline with the traditional data processing pipeline. We have already seen how to build a workflow agent, and now let's take a look at the React agent. The Flink agents provide a built-in class, React agent class, and here React stands for reasoning and action. So unlike building a workflow agent where you need to specify in detail what each action does and how they are orchestrated by listening and emitting different events, and React agent would be leave all these details to the framework and the model to decide. So the only thing you need to specify are the chat model setup used for the reasoning and the prompt that it describes the task goals and the available tools and the expected output schema. So notice that since the React agent class is already defined by the framework, we cannot define resources like the chat model setup and tools with decorators and static methods. So in order to use these resources, we need to first register them to the agent environment. Okay, now we have learned how to build an agent with Flink agents. So there's another topic that I'd like to discuss. That is the consistency. So first, let's take a look at Flink's famous checkpointing mechanism. The core idea is to make periodical checkpoints when processing the event stream. And when a failure happens, Flink will restore everything to when the checkpoint is made and replay from there. So this means that the events between the failure and between the last checkpoint and the failure are actually processed twice. But since the results of the first processing are discarded, so it can still guarantee that the output of the processing is an outcome of each event being processed only once, exactly once. So that is exactly once output consistency. However, things are different for the AI agents. So the agents can automatically take actions, and those actions may have side effects on the external world. For example, sending an email or making a payment, those things should not be repeated. So for agents, we need to make sure that each action is only executed once. So the side effect of the action only take place once. And this is called exactly once action consistency. And to achieve this, we leverage an external action state store. The core idea is to remember which actions have been executed and their results, so that during the replay, we can skip the execution of the actions and get the results directly. So the results consist of updates to the memory and also the emitted events. Here in this example, we have an agent that contains 4 actions. And action A is completed. It has a change S1 to the memory, and it has also emitted 2 events, E1 and E2. And we store that information into the action state store. And event E1 and E2 will also trigger action B and C. And while B is still in progress, here C is also completed. And it makes an update S2 to the memory and also emitted the event E3, which should trigger action D. So we also record that information into the action state store. And let's say we have a failure at this moment, and the agent is replayed from a latest checkpoint. And when the framework tries to replay action A, it will discover from the action state store that A has already been executed. So in this case, it will skip the execution of A, and we simply apply the memory changes S1 to the memory. And also, because the memory is based on Flink state, so it is also restored to when the last checkpoint is made. And then we emit event E1 and E2 to trigger the downstream actions. And we do the same thing for action C. So in this way, we can guarantee that each action is only executed once. Okay, that's pretty much the technical highlights of Flink Agents 010. And for the future plan, we have some future plans. So the top priority is that we will try to apply Flink agents in some real production scenarios to collect feedbacks and identify functionality gaps and also verify the framework. And in addition to that, the exactly once action consistency also need to be enhanced. So currently, it assumes that the action execution is atomic, which is not always true. So we need to be able to dealing with complicated cases, such as failures happens during the action being executed. And also, we plan to add the comprehensive memory supports. So currently, we have only supported the short-term memory, which is insufficient for agents who need to deal with massive memory. So we would need to provide a unified and comprehensive support for sensory memory, short-term memory, long-term memory, as well as knowledges. And last, we also need to support provide multi-agent supports. So currently, you can have multiple agents in one Flink job, but they are in a static DAG, which means one of the agent might always be in the upstream, and the other might always be in the downstream. So what we desire is something like a multi-system demands for dynamic orchestrations, where each agent can flexibly talk to each other. So that's basically the next plan for the Flink agents. So last, some information about the project and the community. Here's a link to the project GitHub repo. So we use GitHub issues for tracking feature requests and also the bug reports. And we use GitHub discussion for some design docs and design discussions. And the user documentation can already be found on the Flink website. And there's a community weekly sync, and everyone is welcome to join. You can subscribe to the Google Calendar and find the meeting records in this GitHub discussion post. And there's also Slack channels. You need to first join the Apache Flink Slack workspace. And if you run into any problems using Flink agents, you can ask for help in the user channel. And the dev channel is for development discussions. So Flink Agent is still a young open source project. So we are looking forward to more contributions, for more contributors to join us to build this exciting framework together. Okay, that's all. Thank you for listening.
Thank you, Shintong. I know we're short on time, but this is such an exciting topic. Can we bring up the lights in the audience? We want time for one question. So does anybody have any questions?
Thank you for the presentation. It was very, very informative. I had a question regarding the one of the extension points that you mentioned at the end, like for supporting multi-agent. You mentioned that currently it's not possible to arbitrarily talk, that one agent can talk to another agent arbitrarily. I remember some time ago there was a project called stateful functions or statefun, where they basically used Flink as an engine for an actor system. I don't know if this project could be reused somehow for supporting multi-agents, or if there is nothing that
yes, it can be reused. Actually, we already reused part of the solutions from stateful functions. So the reason it's not supported is not because it can't be supported, just because it's the first release of the project and we focused on some more fundamental things. Yeah.
Thank you.
I'm also excited to hear that there's the exactly once actions. That'll be pretty cool. All right, let's thank Shintong one more time.
Thank you.